Okay, so let's start. So in the last few classes, we were trying to understand how to solve optimization problems that fall under this broad category, ones that can be posed in this so-called standard form. Right? In the standard form that we are looking at is to minimize some function f0 of x subject to a bunch of inequality and equality constraints. In its full generality, we don't make any assumptions on f0, fi, or hj. They could be arbitrary. But in the case where f0 and all of the fi's are convex and hi's are affine, we call this a convex optimization problem. And I stated some properties of these convex optimization problems. In particular, when we have a convex optimization problem, we have a bunch of sufficient conditions called the KKT conditions, and solving those will give you a solution to this convex optimization problem. Okay, but in general, our goal is to understand when these KKT conditions can be useful and when they're not. Right. So in order to bring up the KKT conditions, we defined the so-called Lagrangian, right? So we introduced a new set of variables called the dual variables or the Lagrange multipliers. Essentially, you have one variable for each of these inequality and equality constraints. So if you have m inequality constraints and p equality constraints, then you have two sets of variables, lambda and nu, where lambda is a vector in Rm and nu is a vector in Rp. Right, so L is from Rn cross Rm cross Rp to R, and this is defined as f0 of x plus a linear combination of the fi's and hj's plus summation I equal to 1 to m lambda I fi of x plus summation j equal to 1 to p nu j hj of x. And from this we defined the dual function, the Lagrange dual function, which is obtained by minimizing out x over all possible x in the domain, right? Not just over x that satisfy these constraints, but over wherever x is defined. So this is equal to the infimum over all x in the domain. This domain is essentially the region where f0, fi, and hj are defined, right? Not necessarily where this is less than or equal to 0 or hj is equal to 0. So it's infimum of L of x lambda nu. Correct? And we saw that this g of lambda comma nu always gives you, at least for lambda greater than or equal to 0, always gives you a lower bound on the true minimum, the actual constrained minimum. So if I define, let's say, f star to be equal to the solution, that is minimum of f0 of x subject to x satisfying the constraints. So let me say that this defines the constraint set C. Then this I'll denote the constrained minimum to be equal to f star. Our goal is to find f star and possibly the x that achieves this f star. Right? And our assumption will be that there exists some x that achieves this f star. Okay, so f star is finite and there is some x that achieves this. That's going to be our assumption. But right now we're making no other assumptions on the entire convex over the entire problem. It need not be convex. Okay, but we saw that for lambda greater than or equal to 0. So component wise greater than or equal to 0. And any vector nu, we have that L of lambda comma nu is always going to be less than or equal to f star. So this always gives you a lower bound. So one way of trying to get the best possible lower bound is to maximize this over all possible lambda and nu. Lambda greater than or equal to 0 and nu in RP. Sorry, that's right. So g of lambda comma nu is always going to be less than or equal to f star. So this automatically means that the supremum over lambda greater than or equal to 0 and nu in RP of g of lambda comma nu, this is less than or equal to f star. So I'll define this to be d star. So this basically gives me another optimization problem. So maximizing g of lambda comma nu is called the dual optimization problem, and that gives me some value d star, and this is always going to be less than or equal to f star. This much we've seen. We've also proved that this is the case. Correct. So in this class we want to see when possibly you can have a gap between d star and f star, and also an intuition as to what d star and f star actually correspond to. We'll see a geometric interpretation of this notion of duality, and we'll see why it is the case that in many convex programs you can actually have zero duality gap. All right, we'll see it of course through some simple examples, but that will also give you some intuition as to why d star should possibly be equal to f star. At this point it doesn't seem like there is any connection between the dual optimization problem and the primal optimization problem. It looks kind of arbitrarily done, right? So one nice way of looking at this connection is to view this through sets, and that will give us our geometric interpretation. All right. So let's consider, we'll sort of fix a couple of simple problems and try to work out those examples by the side, just so that we get some intuition. So let's keep the following convex optimization problem always in mind. So the example that we will keep throughout is, it's a single variable optimization problem, very simple. You can see what the actual answer is. So minimize, let's say x square plus x, subject to the constraint that x is greater than or equal to 1. Okay. What is the x that minimizes this? It's going to be x equal to 1. So if I want to bring this into standard form, this is minimize x square plus x. This is my f0 of x, and I have one inequality constraint, and that is 1 minus x is less than or equal to 0. So what would the Lagrangian be? I only need a single lambda. I have no equality constraints, only one inequality constraint. So corresponding to that, I have a Lagrange multiplier of lambda. Right, so L of x comma lambda is simply going to be x square plus x plus lambda into 1 minus x. Okay. So when framing the Lagrangian, you have to be a little careful. You have to make sure that you actually have a minimization problem. In case the actual problem is a maximization problem, then you bring it down to minimize minus f0 of x. and the inequality constraint should all be in the right direction. So if you have a constraint of the form x greater than or equal to 1, you first bring it down to 1 minus x less than or equal to 0, because that will ultimately influence the sign of lambda. Okay, so this is L of x comma lambda. What is g of lambda equal to? So how do you get g of lambda? You basically minimize for all x in R of x square plus x plus lambda into 1 minus x. How do you get the minimum? Right now you don't know what is KKT condition. I mean, what we have is an unconstrained minimization problem, right? You just differentiate. First, check that the optimization, whatever minimization you have, is of a convex function, right? This is indeed convex in this particular example. So the minimum can just be obtained by taking the derivative with respect to x and setting that equal to 0. So what do you get x equal to? Correct. Lambda minus 1 by 2. Right? Basically 2x plus 1 minus lambda should be equal to 0, or x should be equal to lambda minus 1 by 2. So this, if you plug this back into this, you get lambda minus 1 the whole square by 4 plus lambda minus 1 by 2 plus lambda minus lambda into lambda minus 1 divided by 2. Right? What is this equal to? Minus lambda square plus 4 lambda plus 1 whole divided by 4. Is it correct? Plus 1 minus 2 plus 6 lambda minus 6 lambda minus 1. Are you sure? Correct. Yeah. Yeah. Okay, so this is your g of lambda. And how do you maximize this with respect to lambda? Again, you only maximize for lambda over lambda greater than 0. What would that be? What kind of a function is this of lambda? Quadratic, so it is concave, right? It's concave. So what is maximum over all lambda greater than or equal to 0 of g of lambda? How do you find this? Okay, so you can differentiate this and set it equal to 0. What do you get? Lambda is 3, right? And that is greater than 0. So that should be the true maximum. So when you plug in lambda equal to 3, what do you get? It's minus 9 plus 18 minus 1, which is 8 by 4, which is 2. And in this case, the minimum value is also equal to 2. Right? The minimizer was equal to 1. Okay, so let's keep this example always in the back of our mind. Okay. And of course, we'll keep considering the most generalized version, but also keep looking at what happens to this specific example. Yes.
Just to confirm, then we are telling that the minimum value of like f naught of x is 2.
Correct.
Like are we telling that we are telling it like in a way through intuition as a matter. Like
Which one?
Like when we are saying minimize x square plus x such that x greater than or equal to 1.
Correct.
We are ourselves substituting 1 and telling that it's the minimum. Or
so how would you check whether this is actually the minimum value or not? Okay, so let me pose the question to you. When you said that this is the minimum is achieved at x equal to 1, how did you decide that the minimum is achieved at x equal to 1?
like x is positive.
Okay.
Like an addition of yes.
So firstly, it's a convex function. That's for sure. And where is the global minimum achieved? The unconstrained minimum, where is it achieved? It is achieved at minus half, right? So to the right of minus half, what should the function look like? It should be an increasing function. So since I'm looking only in the regime where x is greater than or equal to 1, so for all x greater than or equal to 1, this should be an increasing function, and therefore that is x. That's one way to convince yourself that that is indeed x equal to 1 is indeed the minimum value. So in fact, you take any function of one variable, any convex function of one variable, the minimum should either be achieved at the global minimum, as long as you have a convex constraint, as long as you're only looking within a particular interval, the constrained minimum is either the global minimum or it should be one of the endpoints. Correct. Okay, but that's all of that only works for one-dimensional optimization. We're not making any general statement for higher dimensional optimization problems. Okay, so now let's go back to the general version, right? First understanding, let's try to understand where we get the dual optimization problem from. So first, let's just resort to some intuition. So what do we have? We want to minimize f0 of x subject to a bunch of inequality constraints, x less than or equal to 0, h j of x equal to 0, right? So let me first try to convert this into an unconstrained minimization problem. Right? So let me define an f tilde of x to be equal to, again, I want to first try to define this in terms of some kind of a combination of f0, fi, and hj. I want all of them in a single equation. Okay. So let me define this to be equal to f0 of x plus summation I equal to 1 to m. I'll introduce this new function I minus of fi of x plus summation j equal to 1 to p. I'll call this I0 of hj of x. Right? Where what are these I minus and I zeros? So I minus is a function where I minus of y is equal to 0 if y is less than or equal to 0, and it's equal to plus infinity otherwise. And I0 of y is a function which takes value 0 if y is equal to 0 and plus infinity if y is not equal to 0. Okay. So this ensures that if I pick a particular x which does not satisfy the constraints, then what is the right hand side equal to? Even if one of the constraints is not satisfied. It will be equal to plus infinity, right? Because if one of the constraints is not satisfied, either fi of x is greater than 0 for some I, or some hj of x is not equal to 0. And if any of them are not satisfied, then the corresponding either I minus will be plus infinity or I0 will be plus infinity. Right? But if all of the constraints are satisfied, you pick any particular x that satisfies the constraints, then what are these terms going to all be equal to? This is equal to 0. So essentially f tilde of x this is equal to f0 of x for any x that satisfies the constraints, and it's equal to plus infinity if x does not satisfy any of the constraints. So basically the unconstrained minimum of f tilde of x would be equal to the constrained minimum of f0 of x. So our problem our original constrained optimization problem is equivalent to finding the minimum or maybe the infimum over all x f tilde of x. Okay, but these functions are difficult to handle, right? So instead of having I minus and I0, we'll instead look at linear functions of these quantities. And that is sort of one intuition for, I'll call this f bar of x, which is just L of x lambda nu. So these functions in some sense introduce penalties for not satisfying the constraints. Instead of introducing these hard penalties, we'll introduce soft penalties. So this is equal to f0 of x plus summation over I lambda I fi of x plus summation over j nu j hj of x. So one way of viewing the Lagrangian is like the original problem with some regularizers, as they're called. Right, so these, you can think of these as penalties for not satisfying some of the constraints. It still doesn't give you any intuition as to why duality should hold, right? Because nu j is allowed to be arbitrary, and lambda I, we assume, is always greater than or equal to 0, right? So if fi of x does not satisfy the constraint, if fi of x so it's clear that if lambda I is positive and fi of x is greater than 0, that is, the constraints are not satisfied, then obviously this penalty term keeps increasing. Okay, that's kind of clear. That gives some intuition for this particular penalty term. The larger fi of x is, that is, the more positive fi of x is, since lambda I is greater than or equal to 0, this penalty term keeps increasing, right, which is what we want. But the second penalty term, it's not so clear, because nu j is allowed to be arbitrary. Nu j it need not be greater than or equal to 0, right? It's an arbitrary real value, correct? So if hj of x is not equal to 0, then it's not clear that this will indeed induce a penalty, correct? It would indeed induce a penalty if the sign of nu j were equal to the sign of hj, right? So in that case, this quantity would be positive, and the more you violate the constraint, the more the penalty that you add. Okay. So to see more concretely the connection between these two, I'll define the following set. So given any optimization problem, I'll define the set A as this very high dimensional vector, which is the set of all f1 of x, f2 of x up to fm of x, h1 of x up to hp of x, f0 of x. So this is an m plus p plus 1 dimensional vector. So this lies in R m plus p plus 1. I'm listing all possible values of these constraint functions, not necessarily for x satisfying the constraints, all possible x. I'll, just for convenience, I'll write this as the set of all vector f, vector h, and f0. Okay. With the assumption that there is some x that achieves these values. So so what is the minimum, the constraint minimum equal to in this particular set? Correct? So if I want f star, this is equal to the infimum what are you trying to minimize in your original optimization problem? You're minimizing f0 of x, correct? So it's basically just the infimum of all, let me call vectors, all t such that, let me say, u v t lies in A. And I also want to satisfy constraints. All right. So what can I say about u? That is f1 through fm should be less than or equal to 0. Right. So u should be component wise less than or equal to 0. And basically this is a high dimension, it's an m plus p plus 1 dimensional vector. I'm breaking it down into sort of sub vectors. U should be less than or equal to 0 and v should be equal to 0. Right? You get these from the inequality constraints. And this should be the equality constraints.
So in the definition of the component wise inequality will be depending on the how we define them.
Not really, right? Why do you say how we define?
It's simply the element of u is less than.
Correct. So assuming that the optimization problem is in standard form. Correct. So the constraints are always fi of x less than or equal to 0, hj of x is equal to 0 for all j. Okay. So that's something that is assumed. Okay. Let's see what happens to the example problem that we had. What does that look like? So the original problem was, I want to minimize x square plus x subject to 1 minus x less than or equal to 0. What is my a in this case? So in the example, recall that the example was minimize x square plus x subject to 1 minus x less than or equal to 0. Right? What is A? A is a set of all f1 of x. There's only one inequality constraint. So first list all the inequality constraints, the functions corresponding to the inequality constraints, and then the objective function itself. So A would be simply the set of all 1 minus x comma x square plus x such that x is in R. This is some set. X is in R, right? So A is a subset of R2. What would this look like? What would the set A look like? Yeah? Why? The y coordinate is, why should that be positive? But X is in R, right? So this is the set. Here I'm assuming that X is in R. X can be anything. X can take X is in this particular set. It's allowed to take negative values. So any guess what this set would look like? We don't have to describe it exactly, but geometrically, what would it look like? Straight line. It will just be a quadratic. It will be a curve. That's it, right? So, I mean, in fact, this is it's a parametric curve, right? And you can just change the parameter. So if I set 1 minus x is equal to u, and then what is this in terms of u? So x is equal to 1 minus u. You would simply get this is equal to the set of all u comma 1 minus u the whole square plus 1 minus u for u in R. Right? This is just a quadratic. Let me see if I have that here. All right. Right, so this is what it would look like. It's just a quadratic. For so in this case, yeah, it's whatever u versus this particular thing. This is what this will. So that's not what I wanted. Let me try to plot that. So this is what this would look like. Okay. Again, not particularly important right now, but this is some set. And this is something that I got from the primal optimization problem. Okay. And what is the minimum? Let's try to see what the minimum is with respect to this particular set. Again, for the original problem, what did we say the minimum was? So the minimum of the constrained optimization problem is you look at this particular set. So among all possible vectors for which the first set of components are less than or equal to 0 and the next set of components are equal to 0, what is the minimum value of the last component? So if you had a function of one variable with one inequality constraint, then what would f star be equal to? So suppose you had a minimization problem, minimum f0 of x subject to f1 of x less than or equal to 0, right? So then this set A would be equal to the set of all f1 of x, f0 of x, exactly as we have in our toy example, x belongs to R, right? In this case, how do you find the minimum visually? Yeah, that's okay. I mean, this is whatever u comma t, correct? Look at this particular general version that we have. If you have to specialize this, what would this be equal to? Exactly. So the left half of the of the t axis, right? You find the minimum value of t, right? So in this particular case, maybe this was too wide a range. So let me plot this for a smaller range of u. Let me say -2 to +2. Okay. So you look at the left half of 0. So the minimum value of the function, or the minimum value of the set, okay, the minimum t coordinate, so this is u and this is t along the y-axis. So the minimum value is the actual minimum of the function. In this case, this would be the actual minimum. Okay. So the minimum is equal to 2, exactly as we had previously. Right. So in general, suppose that we have some f. So for a general optimization problem, I could have some arbitrary a. Maybe this is what my a looks like. Okay. This is my u. This is t. Let me draw it a little more weirdly. Suppose this is a. Right. So what would the minimum be? So basically on the left half, right, for negative u, what is the minimum t coordinate that is achieved within this particular set? So that would be at this particular point. Right? So this would be equal to f star. So that is how you would find f star. So you look at towards the left of the t-axis, the lowest point on the t-axis that is achieved by any point in this set, that would give you the constrained minimum. Potentially, yes, you can. Because so far we have not assumed anything about the optimization. Okay, so now let's Okay, so this is your T. So this is your set A. Okay, I'll also define another version of A, sort of the epigraph version of A, which is the following. So let me call this G, which is kind of like an epigraph version of A. So it is a set of all U, V, and T in R M cross RP cross R, such that there exists some X in the domain for which Fi of X is less than or equal to Ui, Hi or Hj of X is equal to Vj, and F0 of X is less than or equal to T. Okay, and in this case, so you can see that A, the difference between this set G and the set A that I defined previously was that previously essentially I had Fi of X is equal to Ui, Hj of X is equal to Vj, and F0 of X is equal to T. Correct? That was the difference. So in other words, if I have a particular set A, how do you get the set G? Essentially everything above the set A and everything to the right of the set A is included. If any point is in A, then all points above that point and all points to the right of that point also belong to G. So if this is my A, I take any particular point, every point above this is in G and every point to the right of this is in G. So my G will look like something like this. This whole region would be your G. If I go to this particular example, right, everything above the curve and everything to the right of the curve would be in G. Okay, so where does duality come into the picture? What do you call this? Is my A. So let me start with A. P such that Fi of X such that there exists an x for which fi of x is less than or equal to ui, hj of x is equal to vj, and f0 of x is less than or equal to t. Okay. How do you get the Lagrangian or the Lagrange dual function? Remember that g of lambda nu is basically the infimum over all possible x of L of x lambda nu, which, if you think about it carefully, is also equal to the infimum over, if I want to bring it in terms of g, right? What is L of x lambda nu equal to? So let me start with that instead. Common nu. So each x corresponds to some particular point in A. Right? To correspond to some particular point in A. How do you get L of x lambda nu? You can just take the inner product of lambda nu 1 transpose with some particular point, right? UVT. Correct? You would basically get lambda times u, inner product of lambda with u, plus inner product of nu with v plus t. This corresponds to some f0 of x. The inner product of lambda with u would correspond to some summation lambda I fi of x, and the inner product of nu with v would correspond to some summation nu j hj of x, right? So g of lambda comma nu is equal to the infimum of all of these inner products for a given lambda and nu. The infimum value of this inner product lambda nu comma 1 with u v t such that u v t lies in A, but I can also take this to be equal to equal to G. And the reason is because, so G of course contains A, but this only contains suboptimal points of A, right? Because we're looking at all of those points ui for which fi of x is greater than or equal to ui, but all possible x for which t is greater than or equal to f0 of x, right? So I can also take this to be this in G. Okay. So basically what I have is, for a given lambda and nu, this vector is fixed. Correct? I'm sorry, can you repeat? Correct.
We are taking the infimum.
Because I'm taking the infimum. Yes, correct.
Taking the points and they're applying infimum, so that doesn't matter.
Correct. So the infimum over this particular set G is the same as the infimum achieved over all possible, if I take the points from the set A. Okay. So for a given lambda greater than or equal to 0 and nu belongs to Rp, what can I say about this inner product? Lambda nu 1 inner product with u v t. Now g of lambda comma nu is the minimum possible, right? So this is always going to be greater than or equal to g of lambda comma nu for all u v t belongs to G. Correct? Because G of lambda comma nu is the minimum possible of this particular inner product over all points in G. The inner product with any point in G should be greater than or equal to the minimum. So if you look at the set of all possible UVT, not necessarily lying in G, right? So this is some vector. Inner product of this vector with something else greater than or equal to this is a half space. So if I look at the set of all lambda nu 1 times some vector equal to G of lambda comma nu, it gives you a hyperplane. What kind of a hyperplane? It's a supporting hyperplane, right? So this gives you a supporting hyperplane for the set G, right? So the set of all vectors, let me call it, I need something else, let me call it psi, such that lambda nu 1 inner product with psi is greater than or equal to G of lambda nu. So this is a supporting hyperplane for the set G. So I'll come to that. Let's not go to it right away. But all you have to agree at this point is that this psi, this particular set is going to become a supporting hyperplane. Right? So really the interpretation of this Lagrange dual function or the Lagrangian is the corresponding geometric interpretation is that it's a supporting hyperplane for this sort of epigraph. Okay. And what is the maximum value? So let's try to compute this supporting hyperplane for the example that we have. For every given lambda comma nu, it is going to be a supporting hyperplane. At what point doesn't particularly matter. So each lambda comma nu is going to correspond to some point x. It's going to be the supporting hyperplane at some point. We're not going to worry about what that point is. Our only concern is that this will give you a supporting hyperplane. That's it. Okay. So what does the supporting hyperplane look like? Again, let's go back to our example of single function with one inequality constraint. So if we have minimum of f0 of x subject to f1 of x less than or equal to 0, then what does the hyperplane look like? It is a set of all lambda comma 1 inner product with some u comma t equal to g of lambda. Right? So what can you say? So remember, we want g of lambda, right? So what is g of lambda for this hyperplane? Okay, so let me come to that question a little later. Let's try to see what it looks like. So suppose this is our set. So this is my A, and G is basically this particular set. This is your G. Okay. What is the supporting hype? What is it? Again, this, remember that this extends all the way up to infinity. Right? What would a supporting hyperplane look like? It's basically a tangent to this particular, to the boundary. Right? So this would give you so this is one supporting hyperplane. This is maybe another supporting hyperplane, and so on. You can have different supporting hyperplanes. Right? In all of this, what we have to just keep in mind is that the minimum value, that is our f star, this is our f star. Right? Let's just keep that in mind. What is g of lambda equal to? So this would correspond to one supporting hyperplane or one tangent, right? And the tangent is of the form lambda comma 1 plus u comma times u comma t is equal to g of lambda. Correct? So what is g of lambda equal to? If I give you an arbitrary plane, geometrically, what is g of lambda equal to? Yeah? Point of contact with? Are you sure? So this is just a straight line equation, right? So for a given lambda, you have some number, g of lambda is some number, correct? And the equation for the tangent is lambda u plus t equal to g of lambda, right? This is just the set of all lambda u plus t equal to g of lambda, right? Set of all u comma t satisfying lambda u plus t equal to g of lambda. So g of lambda is nothing but the y-intercept. So no matter what kind of an optimization problem you have, as long as it is an optimization problem in a single variable, or in fact the number of variables doesn't particularly matter, as long as there's a single objective function and just one inequality constraint, you get some particular g in 2 dimensions, correct? And for that, the supporting hyperplane will always have this particular form. And for that, the y-intercept will basically be equal to g of lambda, right? So the Lagrange dual function is basically, it just gives you the y-intercept. So each g of lambda will correspond to one supporting hyperplane, and the Lagrange dual function is just the intercept of the t-intercept of this particular supporting hyperplane. Right? This is my lambda, this is my t. Sorry, this is my u, and this is my t. Right? So what is really the dual optimization problem? You want to maximize g of lambda. D star is the supremum over all lambda greater than or equal to 0 of g of lambda. So what does that mean? So you look at all possible tangents to the boundary. What is the maximum value of the t-intercept that you can get? That gives you d star. Right? In this case, what would d star look like? Would it be equal to f star? You just look at the shape of g. Alright, so g looks something like this. This is your so g looks something like this. It's vertical, comes like this, and this is the set G. This is your f star. Right? Is it possible for some supporting hyperplane to intersect the t-axis at f star? What do you think? It's not possible, right? So, in fact, the best case that you can possibly have would be possibly something like this. So you'd get an intercept which is, maybe this would be your d star. Which one? Parallel to x. Would that be a supporting hyperplane? What is a supporting hyperplane? The entire set should lie on one side of the hyperplane, right? So it's impossible to have a tangent that passes through f star and contains the entire set. Above it, yeah. So this would include this as well. That's correct. All right. So this would be a case where you actually have a duality gap. So in this case, d star is strictly less than f star. So this whole notion of duality can be interpreted geometrically, just to recap, in the following way. So you have the set G, which is this sort of epigraph description, as the epigraph obtained by looking at all of the possible functions. The Fi's, in this case, we're only looking at one inequality constraint. So it is Fi and F0. Right? The epigraph of Fi F0 gives you G. And the point where this intersects, so if you think about it, the intersection of the G axis, the lowest intersection of the G axis with with the T axis of G will give you F star. Okay. So F star is actually equal to the minimum overall T such that 0, 0, T belongs to the set G. You can verify this later. So that is what gives you the solution to your primal optimization problem. What about the dual optimization problem? Each G of lambda, for each lambda, lambda comma nu, that corresponds to one supporting hyperplane. Right? And the intersection of this hyperplane with the T axis gives you, at least in only in 2 dimensions, this gives you the value of G of lambda. So the highest intercept that you can have for any supporting hyperplane of this particular set, that gives you D star. And if these two are not the same, if F star is less than D star, then you get a duality gap. So you have strong duality if F star is equal to D star. So just by looking at this picture, right, if you had to guess when strong duality could possibly be achieved, what would be your guess? So if the set G were convex, then you would guess that possibly this is going to achieve zero duality gap. Right? That's of course true in when you have one inequality, of course, in this nice little example that we have over here, but that's not always true. A sufficient condition for strong duality is the so-called Slater's condition. This is called Slater's condition. And it states the following. So as long as, so for a convex optimization problem, and the following holds. So there exists some point x that lies in the relative interior of the domain, the region where all of the Fi's and HI's are well defined. So if there's some point in the relative interior which satisfies all of the inequality constraints with strict inequality, right? If this is satisfied, then the problem satisfies strong duality. It's a sufficient condition, right? Because there are a number of non-convex optimization problems which also satisfy strong duality. Okay. Now, so what you have to keep in mind is that just because the problem is a convex optimization problem, it doesn't necessarily mean that strong duality is satisfied. But in general, it's in most nice problems, this Slater's condition is indeed satisfied. So here's an example of a problem where you don't have strong duality. There is a non-zero duality gap. So consider the following problem. Minimize e to the power minus x subject to the constraint that x square divided by y is less than or equal to 0, and the domain where this is defined is your D is the set of all x comma y such that y is greater than 0. Okay. So first I'll leave it as an exercise for you to show that this is a convex optimization problem. Okay. But let's suppose that it is. What is the minimum value? Can you guess? Yeah. Once at x equal to 0, right? Because e to the power minus x is a decreasing function, right? But when is this constraint satisfied? At x equal to 0. That's the only point that can satisfy the constraints, right? And this is a case where Slater's condition cannot be satisfied at all, right? Because you can't have x square by y strictly less than 0 ever. Okay, so the minimum, so f star is equal to 1. But let's look at the Lagrangian. There's one inequality constraint, which is, so e to the power minus x plus lambda x, so x square by y. Right? So this should be L of x, y, lambda. What is the minimum of this overall x comma y? The infimum overall x comma y in D e to the power minus x plus lambda x squared by y. What would be the minimum value? 1 plus y over D, remember. Can you get minus infinity? Remember what is D. So D is the set of all x comma y for which y is strictly greater than 0. Why do you say it's 0? So firstly, this function is always greater than or equal to 0. That's something you have to, for all x comma y in D, this is greater than or equal to 0 because e power minus x is a non-negative function. x square is non-negative, and in the domain y is always greater than 0. Okay, so is it possible to achieve 0? You can. So again, you have to be careful about the dependence between x and y. So suppose I take y equal to x cube, right, or x to the power 4 maybe. Okay, then I get lambda by x square, and I let x to tend to infinity. What happens? The first term tends to 0, the second term also tends to 0. So this is in fact equal to 0 for all lambda greater than 0. That's one crucial thing. Lambda should be greater than or equal to 0. Right? So g of lambda is equal to 0 for all lambda. So what is d star? 0. But f star is equal to 1. But this is kind of a weird example because I artificially defined this particular d, right? And there was exactly one point that satisfied this. So, but that's always, you always have to be a little careful. In most nice problems, Slater's condition is satisfied, but there are extreme examples where it's not, in which case you don't have strong duality. So if you just try to solve for KKT conditions, you won't get the correct answer. So it was originally stated for, so Slater's conditions, so these are called Slater's conditions. Strong duality holds if Slater's conditions are satisfied for convex functions. But in certain special non-convex optimization problems, you can also check whether these conditions are satisfied. And for certain classes, it turns out that this is also sufficient for strong duality. But it's not true for general non-convex optimization problems. So you can extend this beyond convex optimization to specific subclasses of non-convex optimization problems. It is sufficient.
And the problem is convex load.
It's not necessary. All right. So this. So for general problems, if it's convex, then KKT conditions are sufficient. So if strong duality holds, then KKT conditions are necessary to get the actual solution. So this is conditions for strong duality to hold. Okay, so let's stop here. Any questions?